Hello, this is tutorial number 2 for visual analysis, and in this particular project what we're going to do is build upon the girder that we modeled in tutorial number 1. So for this particular problem we want to reconsider the 36 by 231. We're going to add cover plates near the interior supports, and we're going to add hinges to the beam, and then apply a truck loading to the girder and do an analysis of that. So specifically, we're going to have cover plates that are 15 inches wide by 5/8 inches thick on the top, 18 inches wide by 11/16 thick on the bottom. Those cover plates are going to be 15 feet long, centered over the interior supports. Then 15 feet to the right of support B and 15 feet to the left of support C, we're going to add hinges, and then we're going to add the HS20 truck loading as well, including impact and a girder distribution factor. When we get to the loading part, we'll define the details of the HS20 loading a little bit more specifically. So let's go ahead and get started. Okay, so what I'm going to do is start off with the file that I had from the first tutorial, and the first thing I'm going to do is save it as a new file. So I'm going to save project as, and here I already ran through a dry run once, so I'll call this example 2 XB just to differentiate it from the first one. All right, I don't want to overwrite the first file, especially if I make a mistake or something of that nature, and don't want to goof that up. So let's look through the tutorial here. We're going to start with a model constructed in the previous tutorial for step 1. For step 2, what I'm going to do is I'm going to split the members. So we have to do two things. First off, we have cover plates that extend 7.5 feet to the left and right of the interior supports, and then I have the hinges. So at the start and stop point of those locations where the cover plates are at, I need nodes. Because I'm going to define a different cross section. I'm going to have the W36 by 231 over most of the length of the girder, but in the region where the cover plates are there for reinforcement, I'm going to define that as a different cross section. So I need to have nodes where the cross section changes, and I also have to have a node where the hinges are located. So I'm going to go into this model. Just for sake of clarity, I'm going to go and turn off the load details so they're not shown, and that makes the image a little bit cleaner. Then I'll go ahead and select this node here. I go to the structure tab and I want to split those members. So just one member actually. So I don't want it to split in equal segments. Instead, I want to specify the length. And if I want a node 7.5 feet to the left of node 2, then I would need this to be split at a length of 52.5 feet from the first node. And you can see that node appeared where it was supposed to. Let's go ahead and do the same thing for node 2. In this case, I want to split it into a number of different lengths. So I want to have, let's see, 5 different segments. And I want one at 7.5 feet. Then I want another node 7.5 feet from that. The middle section should be 45 feet long, and then a node 7.5 feet from there. So execute that, and that looks good. And finally, for the last one, we're going to split this one into 2 segments, and I want it 7.5 feet from the first end. Okay, looks good. All right, now the next step, step 2B, is to define the cross section. So in visual analysis, there is a shape builder that allows you to build up cross sections from different primitive geometries, but we're going to use the user-defined cross sections. The shape builder in visual analysis is not free. You can download a copy of it and evaluate it for I think 7 days or maybe 14 days, something like that. But ultimately that evaluation license expires, and it's not free even for educational purposes. I played around with it once. It's kind of cool. If I were a practicing engineer and I was using visual analysis, I would probably go ahead and invest in that, but it's certainly not worth my money right now. When we get to SAP 2000, SAP 2000 has a shape builder built into it that comes with the program. So we can use that when we get there. All right, so I dragged windows across these beam elements. I'm going to change their cross section. So I hit Shift and then drag the window for the first one, hit Control Shift, drag a window for the second one. Over here in the project manager, it's defaulted to modifying the nodes, but I really want to modify the members. And then here under the shape, I'm going to go to a custom blob, which is kind of a funny name, but that's what they call it, just a custom blob. So I'm going to rename it, call it a W36X231 with cover plates. That's kind of a longish name, but you guys, you can name it, with CP or whatever you want to call it, reinforced section. So if you scroll to the end of the tutorial, then there's, at the end of the handout, rather, there's some section property calculations that you guys certainly could have done on your own. So I won't cover those in this video tutorial. I'm just going to enter in the section properties. So I1 and I2 are the strong axis and weak axis moments of inertia, respectively. So this is 23,070. For the weak axis, it's 1450. And then the rest of the numbers really don't matter too much. We're not calculating stresses. We're not using the polar moment of inertia or anything like that. So I'm just going to leave those all defined as 1 like that. Okay. All right. So then we can go to the model filter. For the member details, I'm going to hide the names and leave the shapes shown. So if we zoom in a little bit, yeah, so W36231 with cover plates, and then pan over here, W36231 with cover plates. Good. All right, so I can go back to the Home tab, go back to Zoom All, and we're good to go. Okay, next one, that was step 2C, verify that those have been created. Then step 2D, finally define the hinge locations. All right, now what's defined in my model right now as node 7 and node 8 are going to be hinges there. So we implement a hinge by putting releases in one of the two members adjacent to that node. So I'm just going to select the center element, the center member. I'm going to go to the Project Manager tab and look at releases. And I'm going to release the strong axis moment, MZ, at the first end, MZ1. And I'm going to release the strong axis moment, MZ2, at the second end. And so that gives me a hinge to the right of the first node and to the left of the second node. What you don't want to do is you don't want to hinge on both sides of that node. If I clicked on this member here and then put a hinge in like that, and then I go to filters for member details and show the end releases, what I have is a hinge on either side of node 7 now, and that would create a structural instability. In fact, if I go and try and run the model, I get an error message from VisualAnalysis because it says the model is unstable and can't be analyzed. So the problem is that that node N7 is free to spin. It doesn't have any rotational restraint from either of the two members attached to it. So it has a rigid body motion, and that creates a singularity in the analysis of the model. So let me take away that release in that first member, and now if we try and run it, everything runs fine. So you want to have, in this case, just one of the members attached to the node released. And for my purposes, I found it more convenient to release both ends of the center element. Okay, so that's step D. 2D rather. If you wanted to release the right end of this member instead of the left end of the other member, then the results should be identical. If you wanted to release the left end of this member instead of the right end of the adjacent member, then the results should also be identical. Okay, so step 3, the joint restraints that we had in our previous model should be adequate. They haven't changed at all, so we shouldn't have to modify them here. So let's go on. Now we go to our load definition. And step 4 is where we had the dead loads. The dead loads should be adequately defined. We want to add in live loads though. So let's go to the loading tab and then go to load case manager. And if we go here to the service cases, Then we show the empty cases like that. We can click on the L and that gives us our live load. Now what we're going to do is we're going to create 3 load patterns for live loads. So I have a 3 in this text box down here at the bottom. I want to generate 3 patterns. And when we do that, it looks like nothing happens. But if we scroll down to the bottom of this list, it created L number 1, L number 2, and L number 3. 3 patterns for those loads. All right, so let's see. All right, then the next step is the loading, and this is the HS20 loading that we're going to apply. So it's basically a load that represents a semi-truck, a highway semi-truck, HS, and the loads are given there. So we have 8 kips for the first axle, 32 kips for the center axle, and 32 kips for the rear axle. The wheelbase, or the side-to-side spacing of the wheels, is 6 feet, but that really doesn't enter into this problem. The axle spacing is 14 feet from the first axle to the middle axle, and then it varies from 14 to 30 from the center axle to the rear axle. In our case, it's critical to have a shorter axle spacing so we get those loads spaced closer together. So basically an HS20 loading means that we're going to have 3 axles that are spaced 14 feet apart. The first one's going to have an 8 kip load, and the other 2 are going to have a 32 kip load. Now, in order to account for the dynamic effects of the truck crossing a bridge, we're going to multiply these loads by a factor of 1.33. That's called dynamic load allowance, or impact, depending on who you're talking to. And then finally, when we look at the bridge in cross-section, there are a number of different girders that are spaced across the width of the bridge, and it's not the case that one girder carries 1 lane worth of traffic. The girders work together, so in some bridges you might have 1 girder carry half a lane's worth of traffic, so 2 girders carry the whole thing. In other cases, you might have 1 girder that carries more than 1 lane's worth of traffic, and that's called the lane fraction or the girder distribution factor, depending on who you're talking to and which terminology they're using. In our case, that distribution factor is 0.9643. So each of the girders in the bridge is assumed to carry 96% of the weight of 1 truck. All right, so with that, let's go ahead and shift back to visual analysis. Okay, and what I'm going to do is go up here on the ribbon, and I'm going to select load number 1. Now, admittedly, when I created these, I did it a little bit strangely. Load pattern number 1 is going to be the truck in the center span. Load pattern number 2 is going to be the truck in the left span, and load pattern number 3 is the truck in the right span. So really, L number 1 is the truck in span 2, L number 2 is the truck in span 1, and L number 3 is the truck in span 3. So it's a little bit counterintuitive, but let's go ahead and run with that anyways. So I'm going to click on this member, and I'm going to go ahead and add member loads to it. So L number 1, I want it to be a force in the Y direction. And I want it to be at a location, let's see, it's not a uniform load, it's a single point load. And I want it to be, let's see, 8.5 feet from the left end. So I can go 22.5 feet would be the center, minus 14 gives me 8.5 feet. And then here for the magnitude, that is the rear axle of the truck because it's facing to the right. So I'll type in minus 32 times 1.33 times 0.9643. And when I tab out of that window, it does the math for me. All right, so that gives me 1 point load there. Click on the member again, apply another point load. It keeps the same number. It puts the offset in the center of the member, which is where I want the center axle. So I hit OK, and I get that, and it looks great. And then I'll do the last one. So now I want 22.5 feet plus 14. And here I want minus 8 times 1.33 times 0.9643. Gives me 10.26. All right, so there's load pattern number 1. That's my HS20 truck with impact and girder distribution factor applied to the center span with the center axle centered in the center span. Okay, now I can do the same thing over here. So I want to go to load number 2, and it's still grayed out, so I do that on the ribbon up there. Load number 2. I want to apply a member load. Let's start with the rear axle first. So minus 32 times 1.33 times 0.9643. Now here, what I'm going to do is that first span is 60 feet long. So if I take half of 60 feet, the center of it is at 30 feet. So I can take 30 minus 14. That should be the location of that rear axle. All right, now I can put the center axle in. So that's going to be at location 30 feet. And here I can go in and put the front axle in. So this is minus 8 times 1.33 times 0.9643. And this is going to be 30 plus 14 equals 44. And that gives me the truck in the first span. Then finally, I go up here and go to L3, click on this. So in this case, the geometry is a little bit different. We'll do the rear axle first, minus 32 times 1.33 times 0.9643. Here, I'm going to have, let's see, that whole member is 52. Let's see, I would want 30 minus 14 minus 7.5 is what I want. Okay, yeah, 30 is mid-span, 14 feet to the left of mid-span, and then drop off that 7.5 feet that I have in there to accommodate the cover plates. That's right, 8.5 feet. All right, so that gives me the first axle right there. And the second one, same load. This is going to be 8.5 plus 14, 22.5 feet. And this one here is going to be minus 8 times 1.33 times 0.9643. And this case is going to be 30 plus 14 minus 7.5. Like so. All right. So then you can see those in the tutorial window here. And then the next step is to go back to the loading manager and look at the load combinations. So it's set up to use building load combinations, but I don't want to do that. I would use the AASHTO combinations if they were included in here, but I don't see them. So I'm going to create a custom combination like that. And for dead load, I'm going to put in a factor 1.25. And then down here, I'm going to put in a factor of 1.75 on L1. And I'll call this AASHTO strength 1. Oops, oh, there's an I. What did I call it in my tutorial? I've forgotten already. Let's see. Strength 1, number 1. Okay, so like that. All right, I'll do the same thing for number 2. Oops. There we go. AASHTO strength 1, whoops, number 2. So the dead load is still 1.25. Scroll down to the bottom. Here, this gets 1.75. And then finally, number 3. Like such, 1.25 all the way down to the bottom, and 1.75 like that. All right, and then I'm going to go to advanced cases and include an envelope of those results. Okay, click close. We should be good to go with our loads at this point. So at this point, I can go ahead and click the results view. Let me look at my deformation. So I want to show the results on the deformed shape. There we go. So there's the deformed shape. Okay, so here's the dead load deflections for the beam. Let's go ahead and select all of the members and go to member graphs. There's the dead load diagrams. Here's the load diagrams for the truck in span 2, load pattern number 1. Here are the diagrams for the truck in span 1, load pattern number 2. here are the diagrams for the truck in span 3, load pattern number 3. So here's AASHTO load combination strength 1 for the truck in span 2. Here's the load combination strength 1 for the truck in span 1. And finally, the load combination AASHTO strength 1 for the truck in span 3. And then finally, if we take the worst case of those 3 load combinations, we get that for the load envelope. All right, so that is basically it for this tutorial. If you have any questions, just let me know.